Hello, welcome to this MEI M1 video. We're going to look at January 2011 question 6, where we look at the equilibrium of a particle, and this involves inclined planes. So we'll look through the parts of the question first. There's 4 parts. So we start off with a toy sledge, mass 4 kilograms, being pulled in a horizontal line with a resistance to motion. It tells us some information, and then it says we have to calculate the tension in the string. We're given the acceleration, so that's 3 marks. The situations then varied slightly by putting the string at an incline of 40 degrees to the horizontal. They tell us the tension and we have to calculate the acceleration of the sledge. Again, 3 marks. Part 3 and 4 relate to these 2 diagrams. So in part 3, we now have the sledge on a slope inclined at 35 degrees to the horizontal. The string holding it up is parallel to the slope, and we have a resistance to motion acting up the slope. We then have to calculate the tension in the string that's holding the sledge in place. And then finally, we have a sledge held in equilibrium with the string inclined at theta to the inclined plane. We're told that the tension is 25 newtons and the resistance to motion is again still 6 newtons. And we have to do 3 things. Show all the forces clearly on a diagram, work out the angle that would keep the sledge in equilibrium, and also work out the normal reaction. 2 marks, 3 marks, and 3 marks for those. So it's quite a long question. Let's get started with part 1. So toy sledge, 4 kilograms, the resistance to motion is 6. So we're going to do F equals ma in the direction of motion, which is to the right. So the thing that's making it move to the right is a tension in the string. And so we have tension minus 6, that's the resultant force, will be the mass, 4, and it tells us the acceleration of the sledge is 3. So T will be 12 plus 6, T is 18 newtons. So nice easy 3 marks to start there. Moving on to part 2, again we would still have a tension in the string, but it's now inclined at an angle of 40 degrees. And it's telling us that this tension is 25. Calculate the acceleration of the sledge, so the sledge is accelerating in this direction. Same thing again, F equals ma in the direction of motion. Now we need to resolve this t into a horizontal component in this direction, and because we're turning through the angle there, it would be t cos 40 minus 6, and that's equal to the mass 4 multiplied by the acceleration. Now in this case we know t is 25, so we're going to have 25 cos 40 minus 6, and then if we divide by the 4, that will tell us the acceleration, and if you type that in, it works out to be 3.2877, and we'll round that off to 3SF, so it will be 3.29 meters per second squared for the acceleration. Again, 3 marks for that. Moving on to part 3, we have another situation where we're on a slope of 35 degrees, as shown in figure 6.3. So it's this diagram on the left. It's held in equilibrium by a light string parallel to the slope. So again, we're going to have a tension here up the slope. The resistance to motion 6 acts up the slope as well, and we have to find the tension in the string. Now in this case, we've got to remember that because we're on an inclined plane, we'll have a weight acting downwards. The weight is mg, so in this case that's 4g. And remember, if this angle here is 35, then the angle there to the vertical will also be 35 degrees. So to work out the tension in the string, we can resolve either up the slope or down the slope. Doesn't make any difference which we do. I'll resolve down the slope. So down the slope we're going to have the component of the weight, which will be 4g sine 35, and that's the only thing acting down the slope. And then acting up the slope we have the tension, and we have 6 newtons resistance. And that will be equal to mass times acceleration. Well, the acceleration is 0 because we're in equilibrium. And so rearranging this, we're going to have 4g sine 35, subtract 6, and then bring t over to the right-hand side. That's the thing we want. Again, type it in your calculator. We get t, in this case, is 16.484. And if we're rounding to 3SF, 16.5 newtons. Again, 3 marks for that one. Final part of the question. The sledge is now at equilibrium, same as part 3, but now the string is at an angle. Tension in the string is 25, same resistance to motion of 6 acting up the slope, and we have to show all the forces acting on the sledge to start off with. So, we're going to have a normal reaction acting upwards, perpendicular to the plane. We'll have the weight acting vertically downwards, that will be 4G. And then we'll also have that tension in the string, and they've told us that the tension in the string is 25 newtons. So we've shown all the angles there, or the forces, and then we have to work out the angle theta for part B. So again, it's in equilibrium. You can resolve up the plane or down the plane, it doesn't matter which. So in this case I'll resolve up the plane. So this is part B. So resolving up the plane, we're going to have 25 cos theta plus 6 up the plane, and then down the plane we'll have that component of the weight again. So that'll be 4g sine 35, and that's negative. It's the opposite direction. Rearranging this equation then, we'll get cos theta equals 4g sine 35 minus 6, and then divide by 25. So typing the right hand side into the calculator with g is 9.8, and then carrying out inverse cos, we get theta equals 48.748, which we could round off to 48.7 to 3SF. Just got one part of the question left to do, part C. We have to work out the normal reaction. Now if we look at the situation, the normal reaction is perpendicular to the plane, so I'm going to resolve perpendicular to the plane. Upwards we'll have R, and we'll have a component of the 25, that will be 25 sine theta, and then downwards we'll have a component of this weight. This angle here is 35, so it will be 4g cos 35 going in the opposite direction. So we have two components upwards and one component downwards. So for part C, we'll have the 25 sine theta and the R acting upwards, and then we'll have the 4g cos 35 acting downwards, and that has to equal 0 because it's not moving perpendicular to the plane, so it's in equilibrium in that direction. So R is therefore 4g cos 35 minus 25 sine, and we already know theta, we worked it out in the last part of the question, so using the full value. Type that into the calculator, we get 13.315, and again if we round into 3SF, 13.3 newtons. So let's go back to the beginning of the question and look at how those marks are allocated. So going back to part 1, there we go. So to work out the tension in the string, well, we got 1 mark for applying F equals MEI, an accuracy mark for correctly substituting in the values, there is an allowance for sign errors there, and then an accuracy mark for getting the 18 newtons. Moving on to part 2, we get a method mark for resolving. So that's resolving this force here, and then a method mark for doing F equals MA, and then an accuracy mark for getting the correct 3.29. That's a correct answer only. So if you made any errors along the way, you wouldn't get that final mark. Part 3, we get a method mark for doing forces up the slope and forces down the slope. We get a method mark, an independent mark here for getting the component of the weight correct. And then there's an accuracy mark for the final answer of 16.5. Moving on to part 4, we drew on our forces. So for part A, you got 1 method mark if you got at least 2 of the forces correct. And then you got the second, these are independent marks, you get the second one if you get all 3 correct and you don't put any additional forces on there, so any incorrect forces. So 2 independent marks there. For part B, finding the angle theta, we got 1 mark for resolving parallel to the plane, an accuracy mark for correctly resolving all these different components of the forces, and then an accuracy mark for the final answer of 48.7. And finally part C, 1 method mark again for resolving along the plane. You get an accuracy mark for subbing in the correct values, and that is a follow through. So if you got your angle theta wrong, you would still be able to get that mark. And then there's a final accuracy mark, which is correct answer only, for working out that normal reaction. If you'd like to look at any of the other revision videos for this unit or any other unit, go to www.furthermaths.org.uk.